In previous lecture, we have seen linear triangular element, and with theoretical understanding, we discussed about some scenarios where we can use linear tri-element or tet element, and in which cases we should avoid using linear tri or tet element. Now let's talk about linear quadrilateral element. So as usual, we will consider the ideal shape or perfect square shape of a quad element here, and the center of element is no 0 0, coordinate 0 0, and we have four nodes 1 2 3 4 in anti-clockwise direction, and the coordinates are given as we can see here. Okay, so the size of K matrix element stiffness matrix is a degree of freedom per element. Okay. So this is four nodes, so each node has 2 degrees of freedom, translation in X and translation in Y. So total degree of freedom for element is 8. Size of K matrix is 8 by 8. Size of B matrix, B is strain displacement matrix. Okay. So the 3 is number of stress component or strain components, and 8 is degree of freedom per element. And size of D stress strain relationship matrix is 3 by 3. Okay, because we have 3 stress and strain components. Okay, so first, no, the steps in FEA is no, first we need to find B and D. Okay, then we substitute B and D matrix here to get K matrix. So let's start with B. Okay, before B, first step is we have to assume the trial function. So the displacement in X is U and displacement in Y is B. So we can define it as a discrete function, n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. This should be V. Okay. Similarly, V can be written as n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. So shape functions we can write as something like this. So we know the shape function requirement. Okay. It should be, for example, shape function n1. Okay. It should have value 1 at node 1 and value 0 at remaining nodes. Okay. So these two lines, okay, this line and this line, these two lines are passing through nodes 2 3 and 4. Okay, so we can write so this is x equal to 1, and this line is y equal to 1. So n1 can be 1 minus x and 1 minus y. Okay. So if we put nodes 2 3 4 coordinates here, we get n1 as a 0, and if we put node 1 coordinates in this, okay, we get n1 is equal to 1. So this is how we get shape functions. Similarly, we can write shape functions n2 n3 and n4. Now let's say B matrix, which is strain displacement relationship matrix, and we know for 2D case, okay, uh, epsilon 1 1 is given by dou u by dou x, okay, epsilon 2 2 is dou v by dou y, and epsilon 1 2 is dou v by dou x plus dou u by dou y. So here we have dou u by dou x. Okay, we can just simply put u here. So u is, we can substitute u as n transpose, okay, and displacement x displacement vector. By substituting here, okay, we get dou u by dou x as dou n1 by dou x u1 plus dou n2 by dou x u2 plus dou n3 by dou x u3 plus dou n4 by dou x u4. Similarly, we can put v, substitute v here as n transpose v vector, okay, ve, and we get dou v by dou y as dou n1 by dou y v1 plus dou n2 by dou y v2 plus dou n3 by dou y v3 plus dou n4 by dou y v4. Similarly, we can compute this as well. The shear strain epsilon 1 2. So we have two normal strain components and one shear strain components, and this is our displacement vector, okay, which is 8 by 1 for this element. Okay. So oh, now we can find the derivatives of n1, n2, n3, n4 with respect to x and y, and we can put values here. So dou n1 by dou x is no, minus 1 plus y, okay, divided by 4. So we can substitute all this derivative, okay, and we get the matrix as something like this. Okay. So this is a relation between strain vector and displacement vector. So this is our B matrix. Now before moving to D matrix, okay, let's talk about some observation from this B matrix. So epsilon 1 1 we get by multiplying this row with this column. Okay. So epsilon ij, which are epsilon or strain components, they are not constant through element. So let's try to understand here. Okay. So in FEA, what we do first, we find the unknown displacements. Okay. Uh, by applying loads and boundary condition in FEA algebraic equations, we get u1, v1, u2, v2, u3, v3, and u4, v4. So once we have displacements, we can compute the strain components using this relationship. Okay. So if we observe epsilon 1 1, okay, is uh, is a function of y. Okay. Similarly, epsilon 2 2 is having the x, okay, and similarly epsilon 1 2 has is a function of x and y. So we can say that epsilon 1 1, which is x direction strain, okay, it varies linearly along y direction because epsilon 1 1 is function of y. Okay. And similarly, epsilon 2 2 y direction strain, it varies linearly along x direction. So let's try to understand with this simplest example. Okay, we have this one single element, single quad element. Okay, this is 0 0, and under the pure bending moment M. Okay, this is the deformed shape. So the top edge of the element is under compressive stresses and strains, and the bottom is experiencing tensile stresses. So epsilon 1 1, okay, which is x direction strains. Okay, if we plot through thickness, okay, along y direction, okay, we get the plot something like this. Since it is a linear function, we can say it is a linear function of y. Okay, we get a smooth gradient of epsilon 1 1 along y direction. Okay. So if you remember, if you can recall the linear element, okay, it is the constant strain element. Okay. We need very highly refined mesh to in order to capture the stress gradients. But since the linear quadrilateral element has is already no linear, it already captures the linear variation of stresses and strains through element. It captures the bending stresses very well. Okay. So we can say here that this element captures bending well, unlike linear triartet element captures bending well. So how this comes, we will see in more detail, okay, in chapter next chapter, where we will also talk about different variations of uh, quadrilateral element or hex element, okay, that is full integration element, reduced integration element, We will also see incompatible mode element. So there we will discuss all these in detail. So in this uh, lecture, the objective was to basically understand the difference between, or basically to understand the theoretical difference between linear tria or tet and linear hex element. And what we have concluded is that the linear quad element captures bending well compared to linear tria element, okay, with fewer number of elements. Okay. Other thing, also we talked about double integrals. Okay, so before that, now let's talk about B matrix. We talked about this. Now we will talk about D matrix. Okay. So which is a straightforward. It is a stress strain relationship. So it is whether 2D or 3D, depending on that, we get D matrix. So since we are talking about 2D plane strain case, the D matrix is given something like this. Okay. And substituting D and B, okay, we can get element stiffness matrix. Okay. So we are not going to derive complete, no, we are not going to perform this matrix multiplication and taking integration and computing the stiffness. Okay. So that is something is well understood. So the main point here I wanted to highlight is double integrals. Okay. So once we have this B, D, B transpose D and B, we do a multiplication and we get 8 by 8 matrix here. Now the double integral of matrix is double integral of each term in the matrix. So this double integral will go, okay, into the matrix, okay, and T is outside. So what no we can say here, okay, it has 8 by 8 matrix. Okay, so the thing is we need to perform double integrals 64 times, okay, in order to get stiffness matrix of single first order quadrilateral element. So we can imagine know how computationally uh, tedious okay, it is to get element stiffness matrix. And here we are only talking about 2D element. Okay, let's see some other element types. Okay, let's talk about second order quadrilateral element. This element has nine, or not nine, it has eight number of nodes. So 8 into 2 degrees of freedom at each node. So this is 16 degree of freedom per element. So the K matrix element stiffness matrix for second order quad element, the size is 16 by 16, which is 256. So we need to perform 256 double integrals to get element stiffness matrix of second order quad element. Similarly, now let's take the first order, okay, or linear hex element. So linear hex element has 8 number of nodes. Okay. Okay. So 8 into 3 degrees of freedom, translation in X, Y, and Z. So we get 24 degree of freedom per element. So the K matrix size is 24 by 24, which is 576. So we need to perform 576 double integrals only for single element. So the point I am trying to highlight here is okay, uh, the double integrals are very tedious. Okay, I mean we can see like no, how many integrals depending on element types, how many double integrals we need to perform. Okay, and this concept now we will again recall in our next lecture, that is on integration or Gauss points. Okay. So we'll discuss this concept again.